start it up here. Welcome everybody to training today. Today we're going to focus mainly on heat exchangers, heat transfer. Just for everyone's information, we've added a few more people to the Hurley engineering team, Dave being one of them, Dave and Michael Bacon, and um, others to our engineering side of things where they can help us with more technical and more advanced trainings as we go. So hopefully in the future here you'll see more of this type of training from us. And we really appreciate you taking the time and your support that you give Hurley, and hopefully from these types of trainings we can be a better support for you in your projects and in the field. So with that, Dave, how long have you been with Hurley now?
Oh, just over a year. Been in
Okay.
the Pacific Northwest my entire career, well, after the Navy, and been in the HVAC business for just over 30 years.
Okay. So you probably speak engineer pretty well by
Pretty
then.
good. I'm a professional
Yeah.
mechanical engineer. Haven't done any, stamping for many, many years, but worked with mechanical consulting engineers for the entirety of that career. So yeah, I think I speak
Okay.
their language.
Great. Well, we look forward to it. We probably got a little mixed crowd here, Dave, just so you know. And please use the chat box, everyone, for questions. We'll try to address your questions as they come up. If not, we'll leave a few minutes at the end to address anything we haven't got in the way. And just for housekeeping purposes, Dave will take the first part of this training, and then I'll jump in towards the end to talk a little bit about Alpha Laval, and then we'll do some selections online with the online tool that you'll all have access to. And I've added that address in the chat box for everyone to view. So with that, I'll let you go ahead, Dave, and get started. Appreciate your time.
And thanks, Mike. And again, I'm Dave Greenhack with Hurley Engineering. And like Mike said, I'll be going over kind of the fundamentals of gasketed plate heat exchangers and kind of the do's and don'ts, what to look out for, what you need in a manufacturer. Even the part that Mike talks about that's more Alpha Laval concentric, it's going to be applicable to anybody. So I hope you find it useful. With that, I'll jump in. So there are many types of heat exchangers, both, air side. Here we've got heat pipe, plate exchangers, wheels, and the water, fluid, liquid side, coaxial exchanger. You see these in water source heat pumps a lot. Chill and tube, and of course the gasketed plate. We're going to focus on the fluid liquids and the gasketed plate. Although we have a full line of brazed plate products, including SWEP, and we have shell and tube exchangers. But today we're going to focus on plate exchangers. So actually the brazed and the gasketed apply for the first part of the presentation, and then the second part will focus on the gasketed plate, and then finally finishing up with selections by Mike. So the purpose of the heat exchanger is to transfer as much heat as necessary but at the same time minimize losses and approaches. And some other goals are to minimize the space required, the cost to provide and install, and also very important, the exchanger should be reliable and easy to service, in addition to being efficient to operate. So we've geared this to the why, what, and how. So you make sure you get the right exchanger for your application. A little way back time machine, we'll talk about the three laws of thermo. First, you can't create or destroy energy, just transform it. Second law, total entropy of the universe is always increasing. And third law, that entropy is wanting to go, for a substance wanting to go to zero. So from that, I'd just like to say, obviously, whatever goes in on one side of the exchanger is coming out on the other for equation purposes. So the wet side, the hot side will equal the cold side. There is a little bit of losses through the casing, but as we say in engineering, it's negligible. So when you want to figure out one side to the other, they're equal, right? You put in so much on this side, you're going to get that exact amount on the other side in terms of our selection software. They do account for a little bit of losses, but it's virtually identical. So also, just as obvious as this seems, hot always goes to cold, not the other way around. And when you get involved with complicated systems or there's trouble or you have to troubleshoot a system, it's always good to remember those basics. Can't create or destroy energy, and hot goes to cold. And we see that in other forms in physics, just like fluid. It goes from high pressure to low pressure, and voltage as well, or current flows when there's a voltage difference. So back to the gasket plate heat exchangers, we have different types of heat exchangers. Co-current, which is also known as parallel flow, same direction. Countercurrent or counterflow. There's cross flow and hybrid. We're going to focus on the counterflow, or what others might call countercurrent. And just to make it a little more easy to understand, I'm going to play a quick video, an animation showing that in action in counterflow. So you can see the red is the hot side or hotter fluid. There's the cooler fluid. And you can see they pass along each plate, but one pass and it's done. This is an illustration of counterflow in three different arrangements. The first one is one you just saw in the animation. That's a single pass. So red being the warmer of the two fluids. You can see it goes through each, plate path, each gap, but only once, collects and goes back out. Same with the cooler fluid, or the fluid receiving the heat. Here, this second image shows a multi-pass. And so we put in blank offs. In this case, it'd be right about here in this plate. And it forces the fluids to take one path, collect, and then go back a second path. So series, and you're getting, bigger delta T. That's multi-pass. Both are doing the same thing in this example. And this third example illustrates multi-pass, but with multiple sections. So this thicker black line, vertical line, represents basically a second heat exchanger, all married up in the same package for convenience, but it's a separate exchanger. And the hot fluid is doing that series, two passes, collecting here, and it is continuing on to a third series pass. But the cooler fluid, maybe this is glycol and this is not, maybe this is at 20 degrees or colder, that is in its own section making its own pass. So single pass, multi-pass, and multi-pass with multiple sections. So you see this in process a lot. Here's an animation showing multi-pass. So you can see same, the warmer fluid taking its path. Again, you got that blank off forcing it to take another direction for a second path in series. And the cooler, what's illustrated as a blue fluid, is doing exactly the same thing in opposite direction. So heat transfer, of course, engineers and contractors, even some owners are well familiar with the fact that to transfer heat, you need a temperature difference and surface area. Um, and the K is the heat transfer coefficient, not always as recognizable as the other two, but that's where you get your heat transfer equation. And the LMTD, log mean temperature difference, is basically saying over the course of its path in counterflow, you're getting the most heat transfer as possible. If it was parallel flow, you would see something more like this. You'd get really good heat transfer here, not very good heat transfer here. So counterflow gives us this more even distribution, and it results in, significant increase up to 10% or more over parallel flow. And that's why we do that. This slide is illustrating um, the difference between more plates to get a closer approach um, and the cost that's associated with it. In this first image, they have a lot of plates, costs a lot of money, takes more space, and they have a 1C approach. In the second example, it's 1.5, and here it's 2, so that's about 3.5 Fahrenheit-ish. There is a diminishing return that you will get in heat exchangers, same with towers and other devices, coils and chillers, that you don't get the juice for the squeeze if you keep adding surface area. And in the case of gasket plate heat exchangers and brazed plate heat exchangers, there's other consequences that result from too much surface. So this is a slide depicting temperature in the X from 30 degrees to 120 here on the X-axis, and then the solubility of calcium and magnesium. A lot of minerals, as you warm up the solution, they become more soluble. Not in this case. Calcium and magnesium, they come out of solution, and they'll plate like chrome on a bumper on your plates. So in comfort cooling for HVAC cool temperatures, 40 to 60, you're not going to see as much scaling as fast, but you heat that water up, you're going to get significant scaling, even if the water's pretty clean, not as hard, you'll still see that occur. And so think about like boilers, humidifiers, even cooling towers. You'll get that scale because the temperatures are warmer still. But in any system, this is a problem and it needs to be considered. This image is just showing a system curve, and you can see that as you increase flow, the water pressure drop will increase as well, but it's exponential. It's x squared versus linear. So you don't want to overpump as well. But with gasket plate heat exchangers, it's a balance between going fast enough versus not too fast. Mike, can you hear me okay?
Yeah, yeah,
Great.
hear you pretty good. Yep.
Always tough doing webinars when you can't see people and don't hear anything. So
Yeah,
thank
I've
you.
been watching that chat box and there isn't any questions so far. I thought it was important where you pointed out that when we add that heat, the calcium precipitating out, when we add heat and pressure to fluids, it kind of forces those minerals out, and that's where we have problems if they're not set up correctly.
Yeah, and that frankly is I'd say the biggest problem with plate heat exchangers. They do so well in small space, lots of capacity, um, affordable, but that's the problem, the scale. So chilled water, it works really good in a clean water system. Every plate manufacturer has their criteria and their IOM. It's got to be this pH, no more silica than this, and conductivity, which implies the calcium, magnesium, and other stuff. And if you're running it at 40, 45, 50 degrees, no problem. But now you've got air to water heat pumps, and it becomes a big problem in heating mode. And they'll scale up till they become a brick. And some folks don't even notice it until it's too late, and you're tripping out on high head on the heating mode, or on the water side, you might be doing a low pressure trip on the evaporator. These are the problems that you find when it's too late. You have to maintain these devices regularly, but you don't want to have to maintain them every other month. So, yeah, thanks, Mike, for pointing that out.
Yep.
So again, it seems pretty simple because there's no moving parts, but to do them properly, and design them properly and fabricate them in a way that it's serviceable is anything but simple. There are several plate manufacturers and even more gasket plate heat exchanger assemblers. Um, but there's a big difference in between pressing patterns and versus having a high performance exchanger with a high degree of flexibility. So this slide is illustrating the fact that more is not better. So there's the performance on a plate, and we'll go through all the variables that lead to more performance, less pressure drop, these kinds of things. Um, and the plates just add capacity, but you don't add a bunch of plates to solve your capacity problem, because then you can go into a situation where you have low velocities with less turbulence, which produce fouling faster. And that reduces your performance and has you having to clean them more frequently. The same goes with the channel gaps. If you only have one depth of channel, one depth option, then it may be fine for certain applications, but others it may be too slow. So it's important to pick a manufacturer that has a lot of variability and that they have certified their performance. So this slide is, you can see right in the center prominently here is the HRI certified label for manufacturers that participate with HRI. And think of HRI as like the refs, the NFL owners, team owners. Somebody's got to keep it fair. And when you're doing industrial jobs, you're direct to owner, and you have a contract to do exactly what you say you're going to do. But HVAC is different. We're making a lot of product ahead of time. It's standard product. And, in the old days, it's like the Wild West. Some folks didn't know how to rate them and they'd have falsely high values. Others maybe were trying to imply they had better than they did in performance. So HRI came along, and if you remember, you subject yourself to independent testing and annual testing, and in return, you can carry the label. And there's a cost associated with it too. So not everyone's doing it. So, this is on the left is an example of alpha Laval printout. And if you're not within HRI conditions or it's doing an industrial application, you'd see this. But if you're doing HVAC and the local jurisdiction requires certification, then you would see this. And we have a product for that.
Yeah, I think most manufacturers now have AHRI certification on their models, but it depends specifically on the model, if I'm not mistaken. So
Yeah,
you
you
want to
are
make,
correct.
yeah, you want to make sure if it's mission critical, you want to make sure that you get that third party
I'm glad
certified
you
unit.
pointed that out,
Yeah.
Mike, because there are several years ago, it wasn't the case, but yes, most of them have it now. Um, but there are very few that have many products that are certified.
Yeah.
Some may only have one, so you have very few options. So that can be a problem.
Yep.
So we found a reputable manufacturer, and they're certified for their performance through HRI. Doesn't mean your search is over. Again, you need to have a manufacturer that has a lot of variability and certifies to that. So these are the key variables to consider in a selection, and be sure to select a manufacturer that offers several options for each of these criteria below, because it exists, it's available. So the plate material, of course, and the plate thickness is driven by the application. Same with the gaskets, right? But depth of channel and the plate pattern, and whether you have a combination of plate patterns is really important to ensure even flow, even distribution, and that you're turbulent in all your operating conditions. So you want a manufacturer that can you can select your plates, but then you can run it at different conditions to make sure that you're covered for those lesser flows. Very important, because you could go into laminar flow or less turbulent flow that could encourage scale if you're doing variable flow conditions. Um, or if you're doing variable or different flows on either side of the plate, the hot side's X flow and the cold side's 2X. Well, if you don't have variability in the patterns on either side, then you would have to select for one, and the other could be, you know, laminar or too low velocity and encourage that fouling prematurely. And plate size, particularly the height, will drive the capacity. So before you even add your number of plates, right? Because there's a number of plates in the rack, as we showed earlier. Um, Focus on the plate performance and height, plate pattern, depth. These will drive that problem. Mike, before I hand it to you, I'd like to go back up. I kind of
Sure.
moved too fast here. Um, Let me find a good slide. Thought I had a good one. I wanted you to steer. Would you mind speaking to, the components?
Yeah, how they make up that plate and frame heat exchanger. You've got your end plates that hold the plate pack in itself. Then you've got some type of uh, a expanding bar or a rack hanging bar at the top, and then you've got bolts that you can tighten in order to meet the tolerance that the factory wants to make sure that that plate pack is closed correctly. Also, depending on the configuration, you'll have all your connection ports on one side, or they could be on opposite ends, depending on your application and if you need a specific type of flow pattern when it goes through that. But each of those plates will be suspended, and then you'll have some type of gasket material, whether it's NBRP or EPDM, depending on the fluids that you're transferring. They're all going to be in there. Make sure that the manufacturer you choose has, gives you those options when you're looking at your materials.
Thanks, Mike. I'm going to go
Yep.
back to, so you can see it, one other image here. Actually, not showing an extension, but you can have capacity in your rack to add more plates. That's a thing. And maybe when we're done, we can show a drawing that illustrates some of that when you do your selection. When
Yes. I'll show them where they can select that too to make sure that you could have that expansion capacity
Great.
available.
Well, I'm going to hand
Yep.
it over to Mike, and he's going to talk about some specifics on Alpha Laval, and just know that other plate manufacturers do things that some others might do things that are similar. Just these are things you should look out for and want in a gasket plate heat exchanger.
Yeah, as Dave mentioned in the list before, you've got different plate patterns and stuff available. You want to make sure your manufacturer has options for you. Most of them will have some type of a chevron pattern whether it's a low angle or a high angle chevron pattern. And when you put those patterns together, plates one on top of each other, you'll get what they call a low theta or a high theta configuration. And when you combine those together, as you can see at the bottom, you get low turbulence, medium turbulence, or high turbulence. And that's pretty important when you're talking about exchanging heat from one, transferring heat from one to another. So you can see that as you put the plates or the chevrons together, you can see that the pattern changes. And with those pattern changes, you're going to have different depths and openings and several different types of openings and depths in order to get your best heat transfer across those plates without having a fouling problem. So when we make a selection from Alpha Laval, we're always getting low or medium theta or high medium theta. It depends on the fluid that we're exchanging. But it's important to remember that when you're looking at heat exchangers and where they need to go and go.
Yeah, and it's nice to have a
Yeah,
program that looks out for you on the
yeah,
fouling and tells you, hey, don't do this or do that. And it recommends these because you want to know that you're optimizing against not just capacity, but pressure drop.
yep, exactly. Yeah. So the theta or what they call theta is all based on that chevron, whether it's a high or a low angle, and you get specific plate gaps through that. As you can see there, a plate gap or your pressing depth. So a small gap gives you a high pressure drop, obviously, and a large gap gives you a lower pressure drop. So they can mix these plates together as we make a selection so that some may be a little higher pressure drop and some may be lower within the same heat exchanger. And then remember that the chevron change is the length of the plate. So a short plate or a short plate is going to be a small gap, and a larger plate is going to have a longer gap so that you have wider um, or lower pressure drops through those. So it's all determined by, your inlet and outlet temperatures that Dave discussed and the log mean temperature difference as we're doing it. So from that, the Alpha Laval will select a specific combination for your configuration.
And it'll give you many options too, which
Yep,
is nice. So like Mike said, a combination of the length of the plate, the depth, the pressing depth, and these theta channel options give you a lot of variability, so a lot of combinations.
yep. Okay. Yeah, different types of gaskets as well. All of them have different properties and temperature ranges. So you'll want to make sure that you get those correct when you're making a selection. And I'll show you where that can be changed on the program fairly easily so that you get the correct uh, gasket for your application because there's a lot of different ways to do it. NBRP, the top one, is the most common because it has such a good temperature range, and it has um, good resistance to most oils and fats and stuff like that. So that's typically what we see. And then EPDMP is another, depending on your fluid, that we see quite often.
Yeah, better with acids and
Yep,
bases, chemical resistance and even better temperatures. So yeah.
yep. Okay. The our manufacturer Alpha Laval does what they call a 5 point um, alignment system. So it's pretty unique to them. Um, it helps you get the plates where they need to be when they're taken apart to clean, or if you have to replace a plate or two. It helps you get that alignment correct. So
Or add
yeah,
capacity. It's
add
easy to take it
capacity.
apart, put it back together. You want to make sure it's easy so it
Yeah.
gets cleaned regularly.
Yeah, and then the different combinations they have, you notice here on their port size, they're not round. That's what they call their omega port, and it creates a curved flow as it comes into the heat exchanger itself, so that we don't get those dead areas in a heat exchanger, and there's a slide here that'll show that a little bit later. And then it gives you that flex flow plate design. So it gives you your optimum efficiency so that you're using as much of the heat exchanger service as we can get. And the offset gasket that sits outside, whether it's clip on or glue in, gives you that maximum heat transfer availability and efficiency.
Yeah, and that one is really unique. I don't know who else does this, but just know if you have very dissimilar flows on, the two fluids, then you want to have different, plate paths. But if you're just pressing a single plate, you're going to get the same path. So one's going to be, a lot slower moving through than the other. And that might
Yeah.
be a problem and lead to scale. The flex flow is that we can make combinations so that both paths have they're specifically designed to that flow. So
Yeah, the nice thing about the making sure it's correct and the right gasket is we're concerned with shear stress inside that plate pack. We want to make sure that we're forcing that fluid within the channels and we create that shear stress so that the flow turbulates and transfers all without causing any issues within inside the pack itself. Here's the points that we usually point out when we're talking about alpha Laval, where they're and with any heat exchanger, when you design it, you want to make sure that you're giving them exactly what they need, and those little extras, such as like bearing boxes, so that those bolts come off easily when you're trying to change packs, and then when you torque it back in, it gives you a little more control so that you can torque that correctly and it won't lock up on you. The T-bar rollers is really an important thing as well, so that you can move those plates in and out um, smoothly. Um, the more they like compact frame design, so that we're keeping the required area smaller and also the required area for service smaller. And we mentioned the clip grip gaskets. They also do glued type gaskets as well. And then the 5 point system we pointed out, which gives you that what they call a steer lock plate alignment. So it assures that you get that plate in the proper position before you start tightening it up. And then um, uh, the sealing system. So when we get that aligned with all those points, then it allows us that to seal correctly. So we're not getting those nuisance pinched gaskets or stuff when you put these back together. So look for those types of things when you're looking at heat exchanger and heat exchanger design. Here it goes over what we talked about before, where you get fouling. We want to utilize as much of that plate as we can. You can see if we have a round um, port and then you don't have that curved flow as it goes into the plate itself, you can have some dead areas and that creates areas of fouling or buildup, whether it's biological or mineral or whatever the case may be inside the exchanger. And on the right, you can see utilizing curved flow. We're guaranteeing that we're spreading that flow out before it goes down the plate so that we get more even flow and have no dead areas within the plate itself. Leads to less maintenance down the road and better heat transfer. Here's a couple. This is a good slide I noticed as well, where you have that underutilized area. So you can see from one side to the other where you can short circuit as that system fouls up, you'll short circuit on the water will take the flow path of least resistance. So it's always going to steer away from the fouled areas and go straight down. So your heat transfer is not going to be as well as it could be.
yeah, and the more it short circuits, the more you'll foul over there. So eventually it's won't be working.
It's going to block completely. Yep.
By the way, a quick note. It's always good to have ports so you can check temperatures and pressures so you can see the performance over time against your submittal. That's a great indication of, you know, when you are scaling up. And it's great when you open for a cleaning to take pictures and say, okay, this has been a year and a half since we bought this. This is what it looks like. Then they're like, well, that's a lot of scale. We'll open it in a year and keep doing that picture and timing so you can kind of fine tune your maintenance cycle.
Yeah, for our service contractors out there to
Yeah.
join us. Yeah,
Yeah, and the
making sure
pressures and
those.
temperature readings are really helpful to know if you're off of performance both or have an excessive water pressure drop, which are both indicators of excess scale. But sorry, Mike, keep going.
No problem. Yeah, gauges on all the ports is really essential, or at least a way you can do some, whether infrared or something where you can check to see what your temperatures are coming out. Just good practice. Okay, next.
Oh, and I interrupted Mike here. The last slide is showing our
Yeah,
oblong opening
Omega
in,
port. Yep.
yeah, and the
You can see that there's no
even distribution.
short circuiting in that type of a port. Yeah, here it shows you a good infrared indication of where we've got some blockages. Um, so you're transferring heat in that first part of the plate and then nothing pack, and then the back end, there's nothing. So there's definitely some issues going on here, whether it's blockage or fouling, and that's going to equate to either higher maintenance costs or higher energy costs. You're going to have to pump it a little more, maintain it a little more.
Yeah,
You're
you
just
might
not.
have to extend your approach. So now
Yeah,
maybe your chiller's working harder. But this is
yeah.
interesting. The if you notice the circular, the standard circle versus the omega port, it helps with two things. The curve pattern coming in with the omega port helps with the plate being evenly distributed, but it also helps to make sure all the plates get even distribution. So what you see with omega port versus a circular standard circle is omega port is going to help make sure that you get even distribution along the entirety of that header. So all the plates are getting, so it's not just getting the plate equal flow, but all the plates equal flow.
Thanks, Dave. I think, is that our last
That's it.
slide?
That's our last slide. So I'll
Yeah, so if you want
share.
to stop sharing, I'll bring up the program and then we'll do a couple selections so everybody can see.
Before you get started, we have a question from Christopher. Will this recording be released after this session?
Yes, it will be you should be on our website within a couple days after we do it in the training section of our website. So look for it there.
Great.
If we can get it sooner or if you don't find it there, let us know and we'll make sure we get you a recording. Can you see that selection program, Dave?
Yes.
Okay. Yeah, so here's where I left everyone in the chat box this website. So it's an online program given by Alpha Laval. It's called PHE Select. This is the page you'll go to. You can also download any reference guides or different things you can find within the program. You can download that here. And then down at the bottom, it's going to give you the different options that you can select, whether it's brazed, fusion blonde, or bonded or gasketed plate and frame. And we'll do a selection in the gasketed plate and frame. So they want you to sign in. Usually you click, they want you to sign in to select that so that we know what you've chosen. And then we can contact you if you have any questions. We'll go to the select on that particular one. And it will give us, it says default folder here. You can label it your own folder or project name, just so they have a record of that as well. And when you print your documents, it will print on those as well. Here we can put up your selection name or whatever you're doing. I'm going to do a domestic water heat exchanger. And then if you have a certain capacity you want, you can put that in here and lock that in. Otherwise, you can put in your temperatures. We're going to do 180, and then you can use the tab. I just hit the tab key to take you to the next port, 160. Then here you can change your fluid, whether it's water or glycol or whatever the case may be. And then you can add your flow rate, just put 60 gallons a minute. Your default is going to be 10 psi. That's going to give us uh, good turbulence within the pack. If you have some limitations, you can put that in here, whether it's uh, 3 or 4 or 5 psi, you can change that here. Our inlet water temperature is 40, and our outlet side is 140. And then it will automatically calculate your gallons per minute requirement on that side. You can notice here, anytime we've locked something in, it shows a locked number. So you need to have at least one open thing, whether it is outlet temperature or your GPM. You need to make sure that those are blank so that the system can calculate that.
And
Now
Mike,
you noticed, yeah,
you can lock and unlock
yes,
variables. Should you
yes, you
want, hey,
can,
I want to fix on this side of that, you can lock it.
yes. And once you've made that calculation, it gives you up here, it gives you your capacity, your BTUs that are available. You notice down here on the left, there's a little product input. So we're going to click on that.
Mike, before you go down, could
Yeah.
you click on the little icon between the two inputs?
Yes. Yeah. And that's going to,
So that helps me because sometimes I put in the numbers wrong, or at least when I started, put in the
yeah.
numbers wrong, and it gives you a good visual. Just
Yeah. Most heat transfer, like HVAC systems, these are going to be more parallel lines. But with domestic, we've got a big temperature difference we're dealing with. So that's where you see that gap. The closer we get to the actual output and your inlet temperatures, the closer that those are going to be. So this will tell you whether you've made a good selection or not.
and can you show them the different fluid types? And it's not really intuitive where you can change the fluids.
Yeah, if you hover over, say on this was our boiler side, we can click on that and it'll bring you up a specific fluid, whether it's ethylene or propylene glycol. And here we could change that, and then it gives you a percentage that we can change it to.
Thank you. And you can do
Yep.
mass flow as well, you guys.
Yep.
Obviously, volume is what we're going to do mostly in HVAC,
Yeah.
gallons per minute, but that's an option too.
Yep. So you can see here it changed my fluid for me. And then I can go in here, and since I know it's a domestic water application, I can click double wall plates and also the plate material. With domestic, we want 316 stainless. The default's always going to be 304. And here's where we mentioned earlier that you can change your parameters if you need to change your design temperatures. If this doesn't meet what you need, you can change that here. And once you get that done, you can calculate your result list, and it will give you a calculation based on, best selection down based on your pressure drop and the properties you've put in. So I can click the one that I want. Well, it's taking a minute. And then it gives you all the information here. The model number, all the requirements, your temperatures in and out, and your connections. Also, this is the place where you'd pick up your technical spec. Since it's online, it gives you many options. So depending on your language, you can do that. And I can print that PDF, and this is what it looks like. It gives you your project reference, anything on your hot side, gives you your connection sizes, any of your design pressures that you may change, and then any information on the actual size and weight of the unit as well. I can also get a drawing from that. I can get a 2D or a step file or a Revit file if I want. Also, um, you can get BIM drawings for some that are available. And this is what you'll get. Um, from there, you can download that to your file and keep that information for you. Make sure it fits within the space you want. And you can see this is all connections on the same side. Gives you all your parameters at the bottom for scheduling as well. Okay. Any questions anybody had on that particular selection? Did you see any, Dave?
No more in the chat. I think this is a nice image. In red, they're showing the bars, the
Yes.
all threads,
Yeah,
and
with the
you
bearing
see it
box.
extends beyond. In this case, there's room for more plates. So when you looked at his selection, it said, I think the first one was 6.8% margin. Well, that
Yeah.
means there's that much extra capacity. You can also designate the frame to be even bigger if you want to add future capacity. So that's a thing there.
Yeah, and from that page, you can go down to where it says extension capacity. Right now, you can put in a required extension capacity, 20% if you want.
And if you don't remember any of these, there's a lot of little info meatballs around there with the eye to tell you
Yep.
what you're looking at.
And it should have changed the drawing for us. It overall length changed, so this capacity changed to the back from what it was before. So you can add that on that page as well. Okay. And here you can add that to your project, and then it will keep track of all those for you. And since you're online and you've entered your information, that can be available to you when you come back for projects that you've already done.
And there's a question from David Hebley.
Uh-huh.
And thanks for sending that. Sorry, the bell dog. Thanks for sending that link. I
Yes.
think that's a better link in. He says, how do you add the test ports? And I want to say that would be like a special case. Normally it's in the field, but Mike, you speak to that, please.
What was that again?
He wanted to know how to add test ports. And I think that's in the field, but we could
Yeah,
do it
that
in
would be in the
special.
field. Yes. On the inlet and outlets in the field.
That's all.
Here's here's where you could grab the BIM objects if you needed one, and it would be there. So we've got just a few minutes here. We can do one more. Um, we'll just do like a chilled water. So CHX1. And this is one I did earlier
While
today.
you're doing that, I've got another question from Taylor. Um, is there a chevron angle considered preferable for institute flushing, chemical cleaning, either in forward flow or reversing flow? And by the way, we are only looking at the chat, not the Q&A. So I'll go to the Q&A because I see someone else put one there. But could you speak to that, Mike?
It all depends on the fluids you're exchanging. Typically, we see um, medium high and medium low theta plates in the designs we do with HVAC. But I know some of the more industrial side of things will see a lot more medium high and medium or high type chevrons, mainly because of that. It doesn't matter which plate you use. They're set up with the gaps so that it makes it easy to clean. I would say a high theta um, plate is probably it's a little flatter curve, so it's probably a little more easier to clean if you had to flush that.
And if you have
Makes
any
sense.
questions about applications. We love to get involved and bounce any of your questions that we can't, that we're not familiar with, we can't answer. We'll bounce them off the factory and get you.
Yeah, we will. In this one, this application we had, we're doing some passive cooling. Um, we had a flow rate requirement that we needed, so we'll leave that one in there and not do the outlet temperature. We'll let the system calculate that for us. And then you can see on this one, like we discussed before, it's closer to parallel, so we've got a good good gap here, and we do have a good heat transfer. So it's not a close transfer. We're just trying to get as much of the heat as we can on one side from the other. And this one needed to be 316 stainless, so I can change that here.
And we have one more question from
Uh-huh.
Nitch Luton. What are the upper temperature limits? It's really driven by the gaskets, I want to say. Is that right?
Yes, yes, it is. And here's where you change that if you've got higher temperature limits. You want to change that here, and that will directly affect the gasket material that's selected and possibly the plate material, depending on the temperature, but most likely the gasket material.
And while we're on it, we're talking 350 degrees Fahrenheit is a typical higher limit.
Yeah,
Um, but yeah, thanks.
yep, on ASME, yes.
Right.
Yeah, you can also click down here on your inlet outlet arrangements where you can change where the hot inlet would be. And then it will change the configuration of the front portion of your uh, plate pack, and it'll also change the arrangement of the plates. So S1 is typically the inlet on the hot side. So if you need to change that because of your configuration, we've had to do that on some data centers and stuff like that to meet the criteria to hook the system up. So just know that that's available for you. And we can calculate our results. Let it load up.
Well, it's loading next to the selection entry on the previous page. There's a radio button for design, and next to it's an option for rating. So once you get what you think is your preferred selection, you can run it at different conditions, hitting that radio button.
Yeah. And here it gives you all your connections here as well. Same drawings, tech spec, we can grab from the same thing and print. And here's where you would add that to your project, and then it keeps track of that for you. Did you see any other questions, Dave?
No, that was it.
Okay. I'm going to stop sharing then. Okay. Okay. Any last minute things, Dave, you think we might want to touch on before we
No,
move
just
forward?
thank everybody for participating, and I hope you got something out of this. And just know that myself, Mike, and the Hurley team are available to help you with, the software program, or do your selections for you, and you can review them, or any odd application. Alpha Valve's involved in everything from utility to marine to industrial to HVAC. So really nothing they haven't seen. And yeah, look forward to working with you.
Yeah, just remember we left you that PHE Select website. Feel free to go in and you give them your email and then just start a project if you want to practice or whatever. We'll get contacted so that we can follow up with you and make sure that if you had any questions or needed to add anything to your system and selection, we can help you with that as well. Yeah, definitely reach out to your Hurley guy and we can go from there. Okay, we appreciate everybody's time. Thanks, Dave, for your insights and all the detailed information. And we look forward to seeing you in the future on some more websites similar to this. Thanks
Thank
again
you,
for
Mike, and
supporting
thank you.
Hurley.
I appreciate it.
You bet. Thanks, Dave. See ya.